p square plus q square into y equals qz. We can solve this nonlinear partial differential equation using Charpit's method. We have f of xy is at pq equals 0 given by p square plus q square into y minus qz equals 0. We will find the partial derivatives dou f by dou p, dou f by dou q, dou f by dou x, dou f by dou y and dou f by dou z in order to write the Charpit's auxiliary equations. We have dou f by dou p equals 2py, which is obtained from the term p square y getting differentiated with respect to p. We have dou f by dou q equals 2qy minus z, considering derivative of terms q square y minus qz with respect to q. We have dou f by dou x equals 0 because there are no terms containing x in this equation. Dou f by dou y equals p square plus q square, taking derivative of term p square plus q square into y with respect to y. We have dou f by dou z equals minus q, taking derivative of term minus qz with respect to z. Having found the partial derivatives, we can write the Charpit's subsidiary equations given by dx by minus fp, that is dx by minus 2py equals dy by minus fq, that is dy by minus of this expression, which becomes dy upon z minus 2qy equals dz upon minus pfp minus qfq, that is dz upon minus p into 2py minus q into 2qy minus z, which can be written as dz upon positive qz minus 2p square y minus 2q square y. Here we can again simplify it. When we take 2 common outside from these two expressions, we have p square plus q square into y. This can be replaced by qz from the given equation in the question. Therefore, p square plus q square into y when replaced by qz, this becomes qz minus 2 times qz. Therefore, dz divided by qz minus 2qz can be written as dz upon minus qz. Now we have the next ratio in the auxiliary equation given by dp upon fx plus pfz. We have fx is 0 here and pfz is p multiplied to minus q. Therefore, dp upon minus pq is the obtained ratio. The final ratio to be written in the Charpit's auxiliary equation is dq upon fy plus qfz. We have fy equals p square plus q square and qfz is given by q multiplied to minus q. Therefore, we have dq upon p square plus q square minus q square. Q square and q square get cancelled. Therefore, we have dq upon p square as the final ratio. When we compare dp upon minus pq and dq upon p square, we have p getting cancelled from both denominators and we get the simplified form minus dp upon q equals dq upon p. When we separate the variables, we have minus p dp equals q dq. After integration, we get minus p square by 2 equals q square by 2 plus constant of integration. When we bring p square to RHS after integration, we have p square plus q square equals 2 times constant of integration. After integration, we get the equation p square plus q square equals c square. This c square may be considered as a constant, which is obtained after multiplying 2 to the constant of integration which we obtained in the previous step. When equation 2 is applied on equation, we just have to replace in this equation 1 p square plus q square by constant c square. Therefore, now 1 becomes c square y minus qz equals 0, from where we have q equals c square y upon z. This is an expression of q independent of p. Using this expression, we will find out an expression for p independent of q. Therefore, we give the expression of q in equation 2 and we have p square equals c square minus q square written as c square minus c square y upon z the whole square. When we take square root on both sides, we have p equals root of c square minus c raised to 4y square upon z square. Inside the square root, when we take LCM, we get z square c square minus c raised to 4y square upon z square. We have c square that can be taken outside from the numerator, and when taken outside the square root, it becomes c. Z square can be taken outside the square root and it becomes z. Therefore, we obtained p equals c by z upon c by z into root of z square minus c square y square. Since we have dz equals p dx plus q dy, we will replace p and q by these expressions p equals and q equals c square y upon z. When we bring z to the LHS along with dz, we obtain this equation. And if we bring c square y into dy also to the LHS, we have this equation. This equation can be rewritten as z dz minus c square y into dy upon root of z square minus c square y square equals c dz. We just brought the expression involving square root to the LHS as denominator. The reason behind this is that if you consider z square minus c square y square, which is the expression appearing inside the square root as t, when you take derivative on both sides, you obtain dt by 2 equals z dz minus c square y into dy. Because of this reason, you can rewrite this numerator by the expression 1 by 2 times derivative of z square minus c square y square. Because the numerator is actually the derivative of denominator along with 1 by 2 multiplied to the derivative expression. Therefore, this numerator can be written as half times derivative of the expression appearing inside the square root. When we integrate both sides, we have the integration done in the LHS in the format half times integral dt upon root t, which is obtained as root t after doing integration. Therefore, after integration, this LHS becomes root of z square minus c square y square, where we had assumed t equals z square minus c square y square. And in the RHS, we have c into integral dx, which is cx plus a constant of integration a. When we square both sides, this can be written as z square plus a plus cx the whole square plus c square y square, which is the required complete solution involving two arbitrary constants c and a.